Hi class, this is Dr. O'Connor. Hope everyone's enjoying the weekend. Here we're going to talk about chapter 4, and this is all about some different types of chemical reactions. We're going to talk about acid-base reactions, precipitation reactions, and oxidation-reduction reactions, also called redox reactions. So what I'm going to do with this chapter, I might divide this up into 2 videos, possibly even 3. So let's talk a little bit about what happens when you dissolve sodium chloride, salt, into water. We all know that sodium chloride is soluble in water. And what happens is when we put the sodium chloride into the water, the sodium chloride completely dissociates into sodium and chloride ions. This is called an aqueous solution. Remember what I told you in class. An aqueous solution is one where there's a solute, in this case sodium chloride, dissolved in water. Aqueous solutions of ions are electrically conducting, so they will conduct electricity. Substances that dissolve in water are called electrolytes or non-electrolytes. An electrolyte is a substance that dissolves in water to give an electrically conducting solution. So, for example, soluble ionic compounds. Remember, ionic compounds are salts. So soluble ionic compounds will dissolve in water to produce an electrically conducting solution. That's because they completely dissociate into ions. Now, it turns out that not all electrolytes are ionic compounds. For example, hydrogen chloride gas, when dissolved in water, becomes aqueous hydrochloric acid. And that's because when dissolved in water, the hydrogen chloride actually dissociates completely into hydrogen ions and chloride ions. Okay, so let's take a look at this figure here, and you can think of this as being the sodium chloride crystal. Okay, so we place that into water, and we know that, again, when we put a soluble ionic solid into water, it dissociates completely into ions. So what we need to do is look at the water molecule. Let me just check something here. Okay, I don't have that. Never mind. So let's take a look at the water molecule for a minute. So sorry, my drawings aren't the greatest, and it's really hard to control with this pen. So I'm going to put electrons here on the oxygen. So this would be our Lewis structure for water. Here's what happens. We know that water is a covalent compound. In other words, electrons are shared between the atoms. But here's what happens. We have oxygen and 2 hydrogen atoms. It turns out that oxygen tends to draw electrons towards itself. So its electrons are going to be more attracted, if you will, to the oxygen than they are the hydrogens. So these electrons in these bonds are going to spend more time around the oxygen than they do the hydrogen. That's going to give a partial negative charge on the oxygen and a partial positive charge on these hydrogens. So what happens is we put the crystal of sodium chloride into the water, and you can think of the water molecules as pulling the ions from the crystal. So the partial positively charged part of the water molecule will pull off the chloride ions, while the partial negatively charged portion of the molecule, the oxygen, will pull off the positive sodium ions. So what happens is each ion is going to be surrounded by water molecules. Here we see a chloride ion being surrounded by 1, 2, 3, 4, 5, 6 water molecules, and a sodium ion being surrounded by 6 water molecules. So that's kind of a basic idea of what happens when we dissolve an ionic compound in water. Now we're going to find later that not all ionic compounds are soluble in water. So sodium chloride is what we call an electrolyte. Okay, so let's take a look at what happens here. Non-electrolytes do not dissociate in water. They do not dissociate into ions. We can have a non-electrolyte, a strong electrolyte, or a weak electrolyte. A strong electrolyte, like sodium chloride, dissolves in water to give an electrically conducting solution. In other words, it completely dissociates into ions. So sodium chloride is an example. There are many other ionic compounds that are water soluble. They would also be strong electrolytes, and strong bases like sodium hydroxide and strong acids like hydrochloric acid will also completely dissociate in water as ions. So strong bases like sodium hydroxide will dissociate completely into ions when placed into water, and hydrogen chloride gas, when put into water, will completely dissociate into hydrogen and chloride ions. Now, a non-electrolyte is a substance that dissolves in water, and it gives a non-conducting solution. The solute is going to be present almost exclusively as molecules. Pure water is one of them, methanol, ethanol, and also sugar. Okay, so these do not produce a conducting solution. Weak electrolytes, on the other hand, are solutes that will partially ionize. In other words, they'll dissociate a little bit. They don't completely dissociate. So in solution, you'll have both molecules and some ions. Okay, these are poor conductors of electricity. Weak acids like acetic acid, here's the formula for that, are poor conductors of electricity. Ammonia, which is a weak base, that is also a poor conductor of electricity. Here we can see that when we put methanol into water, we have this apparatus here. We have a power source, we have a light bulb, and then 2 electrodes in the solution. And notice that when those electrodes are placed into a methanol solution, nothing happens. The bulb doesn't light. That's because there are no electrically conducting particles in that solution. Now notice here, when we put sodium chloride into water and then we put these electrodes in, this bulb lights. Now here we have some acetic acid. We call that a weak electrolyte. It only partially ionizes. Notice the bulb, it lights a little bit, very, very dim light. That's because you've only got a few ions in the solution. The key here is the more the electrolyte dissociates, the more ions it produces, and therefore the greater the electrical conductivity, if you will. Okay, let's go up here. So we'll make some generalizations here, and what we have is the strong electrolytes include strong acids, hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, perchloric acid. Memorize these. Know these. These are the strong acids. In other words, they completely dissociate into ions. Make sure you know the strong acids. There are only 6 of them: know them. You can consider all of the other acids, and again, we're just talking about acids in aqueous medium. All of the other ones you can consider weak acids. These are the strong acids. Everything else consider weak. Phosphoric acid is weak. Sulfurous acid is weak. Hydrofluoric acid is weak. Strong bases. These are groups 1A and 2A hydroxides. Okay, so potassium hydroxide, sodium hydroxide, these are strong bases. And they're strong electrolytes. They completely dissociate in water. Most of our water-soluble ionic compounds, our salts, are also strong electrolytes. Weak electrolytes include weak acids, like the acetic acid, and we have some weak acid. Here's hydrocyanic acid, acetic acid, and there are some very few ionic compounds. We'll talk about those later. Non-electrolytes include most molecular compounds, your alcohols, ketones, sugars, and most organic compounds, because most of them are molecular, but there are a lot of exceptions to that. Let's take a look at the dissociation of calcium chloride. So we have calcium chloride, we place that into water, and that completely dissociates into calcium and chloride ions. Notice how this equation is balanced. So let's take a look here at how to calculate ion concentrations in solutions. By the way, when you see the formula of a compound or a polyatomic ion in brackets, those are used to represent molar concentrations. We haven't talked about molarity yet, and I'm going to do that right now. Let's talk a little bit about molarity. Molarity. This is a concentration unit, and molarity is represented by a capital M, and that is equal to the moles of solute per liter of solution. The solute is the substance that's being dissolved. It's usually present in the smaller amount. And the solvent is that does the dissolving. And for aqueous solutions, the solvent is water. And that is usually present in the larger amount. The solution includes both the solute and the solvent. Okay? If I tell you I have a 2 molar solution of sodium chloride, so I have an aqueous 2 molar sodium chloride solution, what this means is that I have 2 moles of sodium chloride for each liter of solution. Notice, I'll rewrite molarity here. Molarity equals moles per liter. Notice I can actually use this to determine the number of moles if I know the molarity and the volume. If I know the number of moles and the molarity, I can determine the volume I need. So this equation is something that you need to know. So let me show you how we would make a 2 molar solution. We use the term molar when describing the solution. So, I have a solution that's 3 molar sodium chloride, 5 molar hydrochloric acid, and so on. So here is what I would do. I'm going to go ahead and erase this. So let's say I want to make that 2 molar sodium chloride solution. I need 2 moles of sodium chloride, and I'm going to have to convert that to grams. I have to do that because my balance in the lab only measures in grams, not in moles. So the molar mass of sodium chloride is 58.44 grams per mole. And if I need 2 moles, that would be 2 times 58.44 grams. And that would give me 116.9 grams of sodium chloride. So I would measure out 116.9 grams of sodium chloride. And I want to make a liter of this. And this is a volumetric flask. And so if this is a 1 liter volumetric flask, I would place the 116.9 grams of sodium chloride in there. I would go ahead and fill that up with a little bit of water. I'd go ahead and shake real well until the sodium chloride is completely dissolved. Then I would go ahead and dilute to the mark with water. And this would give me a 2 molar sodium chloride solution. I could make a smaller amount. Let's say I only needed 100 milliliters. Maybe I don't need a whole liter. Maybe I just need 100 milliliters of 2 molar sodium chloride. Okay. I would go ahead and write out I have 100 milliliters. And I could use the molarity to determine the number of moles. So we know that the molarity is, I have 2 moles, right? 2 molar can be written as 2 moles per liter. And what I could do is I could convert that to milliliters. So that'd be 2 moles per 1,000 milliliters. And 100 goes into 1,000 10 times. And 2 divided by 10 is 0.2 moles of sodium chloride. And 0.2 moles of sodium chloride. We know that 1 mole is 58.44 grams. And that would give me, I would need to measure out 29.22 grams of sodium chloride. And I would put that into a 100 milliliter volumetric flask, dilute to the mark with water, and that would give me 100 milliliters of 2 molar sodium chloride. In the lab, we have many, many solutions. So let's say that in the lab, I have a 6 molar hydrochloric acid solution. Okay. So we have a 6 molar. In the lab, I have this 6 molar hydrochloric acid solution. So here's my beaker. Here's my 6 molar HCl. So let's say I want to make 250 milliliters of a 0.3 molar HCl solution. What I would do is I can use this relationship here. This is our dilution formula. And another way to write it is like this. Here, M stands for molarity. So your initial molarity times initial volume is equal to your final molarity times a final volume. So this is dilution. This would be the more concentrated. This would be the less concentrated. I rewrote the formula like this because this works for any concentration unit, not just for molarity. When using these formulas, make sure that the volume has the same units on both sides. It could be anything, milliliters, liters, microliters, whatever. So let's go ahead and start with this. We need 250 milliliters of a 0.3 molar hydrochloric acid solution, and we're going to get that from the 6 molar hydrochloric acid. So let's define each one of these terms here. So M1 is going to be the most concentrated. That's our 6 molar solution. V1, that's what we're looking for. How much of the 6 molar solution do we need in order to make 250 milliliters of a 0.3 molar solution? M2 is 0.3 molar, and V2 is 250 milliliters. So now I'm just going to go ahead and plug into this. So we have 6 molar, and we'll multiply that by V1. This is what we're solving for. That's equal to M2, which is 0.3 molar, times 250 milliliters, which is V2. Let's go ahead and solve for V1. V1 is 0.30 molar times 250 milliliters divided by, you know what, let's just go ahead and make that 6.0 molar divided by 6.0 molar. Notice molarity cancels out, and we have 0.3 times 250 divided by 6, and that's going to be 12.5 milliliters. So I'll leave that at 12 milliliters. So what I would do is I would have a 250 milliliter volumetric flask. Sorry, my drawing is awful. I would go ahead and remove 12 milliliters of the 6 molar hydrochloric acid, put it into this flask, dilute to the mark with water, and that would give me 250 milliliters of a 0.3 molar solution. Okay, so practice these molarity problems and also the dilutions. Now, let's go back here, and we're asked what is the molarity of each ion. So we have 0.566 molar sodium chloride, and we go ahead and put that into water, and it completely dissociates into sodium and chloride ions. We have a 1-to-1 ratio, so that means we have 0.566 molar sodium ions and 0.566 molar chloride ions. Here we have 0.01 molar sodium carbonate. I'm going to go ahead and write the dissociation here. We put that into water. It completely dissociates into 2 moles of sodium ions plus 1 mole of carbonate ions. So what we have is 2 times 0.1, I'm sorry, 2 times 0.01 molar sodium ions. So that's going to give us 0.02 molar sodium ions, and we have a 2-to-1 ratio of sodium ions to carbonate ions, and that would be 0.01 molar in carbonate ions. Okay, so let's do this one again. I'll go ahead and write the equation for the dissociation. This is in water. This will completely dissociate into 2 moles of ammonium ions plus 1 mole of sulfate ions. So the concentration as far as sulfate ions go will be 0.2310 molar, and for the ammonium ions that would be 2 times 0.2310 molar, and that would give us 0.462 molar in ammonium ions. Okay, so practice those. So now what we're going to do is talk about acids and bases. So we'll talk about strong and weak acids. I told you which acids to memorize as far as the strong acids. There are 6 of them. All the rest in aqueous medium we'll consider weak acids. Here we have hydrogen chloride gas. We put that into water and it completely dissociates into hydrogen ions and chloride ions. So when we have aqueous HCl, that is hydrochloric acid, and it's a strong acid, and it will completely dissociate into hydrogen and chloride ions. Okay, so that means the concentration for a 0.001 molar hydrochloric acid, we're going to have 0.001 molar in hydrogen ions and 0.001 molar in chloride ions. Now, as far as weak acids go, they are weak electrolytes. And for acetic acid here, that's in water, it will dissociate into hydrogen ions and acetate ions, but it will only partially dissociate. So it does not completely dissociate. That's why it is a weak acid. Notice we have the double arrows. This indicates a reversible reaction. So what will happen is the acetic acid, it will partially dissociate into hydrogen ions and acetate ions. And then after some time, the hydrogen ions and acetate ions will recombine to form acetic acid. So you have both a forward and a reverse reaction. What will happen is this will reach a state of dynamic equilibrium, and this means the concentrations of the reactants and the products are going to remain constant over time until that equilibrium is somehow disturbed. So let's go up here. We have acids that are monoprotic, diprotic, and triprotic. So for example, hydrochloric acid, that is monoprotic. It means there is one acidic hydrogen. Sulfuric acid is diprotic. So there are 2 ionizations, one for the first hydrogen. So we'll see here that when we put sulfuric acid in water, okay, that first ionization involves dissociation into hydrogen ions and hydrogen sulfate ions. Okay, so most of that happens in that first dissociation. Okay, the second dissociation is with the hydrogen sulfate ion, and this, notice, is an equilibrium situation. It's a reversible. That's because hydrogen sulfate ion is considered a weak acid. Okay, so it will only partially dissociate into this and this, but what will happen is this first dissociation will account for the hydrogen ion or the hydronium ion concentration in that solution. Now, our strong bases for aqueous solutions, the strong bases are the ionic hydroxides from groups 1A and 2A. Some of the group 2A hydroxides are not very soluble. So, for example, group 1A, lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on are very strong bases. That's because lithium hydroxide, for example, again, it'll completely dissociate into lithium ion and hydroxide ion. It's that hydroxide ion that is the strongest base in aqueous medium. As far as our group 2A hydroxides, we're mainly calcium hydroxide, strontium hydroxide, and barium hydroxide are very strong bases. An example of a weak base is ammonia. Also, some other weak bases are what we call amines. And amines, for example, here's one. This is methylamine, and there is a nitrogen bonded to carbon. Okay, so the amines, these are weak bases along with ammonia. Now, something I should tell you before we go on is that, we talk about hydrogen ion being in solution. That's not quite true. hydrogen ion does not exist in solution. The hydrogen ion will associate with a water molecule, and that produces hydronium ion. Okay, so that is hydronium ion. In your book, they use this and this interchangeably. So this means hydronium ion. Okay, so I'll go along with your book, and I'll use this. But when we get into Gen Chem 2, this is what we're going to see most often. We're not going to see this. As far as bases go, the weak bases, so here we have ammonia, and we put that into water, and there's an equilibrium here between the ammonia, water, and then ammonium ion and hydroxide ion. The hydroxide ion is produced because the weak base, the ammonia, picks up a proton from water, and here we have ammonium ion, and we're left with hydroxide ion. The same here with methylamine. Put that into water, and the methylamine picks up a proton from the water, and here we have the methyl ammonium ion, and hydroxide ion is produced. Acid-base reactions, we're going to talk about neutralization, and this is the reaction between an acid and a base, and the products are water and a salt. So notice here that hydrochloric acid, sodium hydroxide, and sodium chloride are strong electrolytes. That means they're completely dissociated in water. So let's take a look at this by writing the ionic equation. So the acid here, it's hydrogen ion or hydronium ion and chloride ions. The sodium hydroxide is dissociated as sodium and hydroxide ions. Water, of course, is water. It does not dissociate, but the sodium chloride dissociates into sodium and chloride ions. Okay, notice this. Notice we have chloride ions on both sides of the equation and sodium ions. They cancel out, and what we're left with is our net ionic equation. And look at this. The actual reaction is between hydrogen ion, hydroxide ion, to produce water. So these sodium and chloride ions are what we call spectator ions. They are there, but they don't actually take part in the chemical reaction. Remember, a weak acid, that does not completely dissociate. So there would be a different net ionic equation. But for all strong acid, strong base neutralization reactions, this is the net ionic equation. The actual reaction takes place between this and this to produce water. Now in the lab we use indicators. So an indicator, these indicators are acids and bases as well, and we use them to determine whether we have an acidic solution, a basic, or a neutral solution. So phenol red, that's an indicator, and it happens to be yellow in acidic solution, orange in neutral solution, and red in basic solution. Phenolphthalein is another one that you'll use in the lab. And basic solution, it's this same color, and in acidic solution, it is colorless. Let's go ahead and write some net ionic equations for these three problems here. We're asked to write the net ionic equation for the neutralization of hydrochloric acid by calcium hydroxide. So first we write the formula equation. We have hydrochloric acid plus calcium hydroxide, and we're going to go ahead and we're going to form a salt and water. So the calcium, remember what's going to happen. The acid will release the proton, and we're going to end up with calcium chloride, which is soluble, and water. So we have to balance our equations. So I have to put a 2 here, and I'll put a 2 here. So this is balanced. Now, we know this is completely dissociated. This will be completely dissociated, as will this. So let's go ahead and write the ionic equation. So we have this. Then the calcium hydroxide. And we have 2 hydroxides. Okay, and that's going to yield the calcium chloride will be completely dissociated. So we have calcium ion plus 2 chloride ions plus 2 water. Okay. Now, what we can do, we notice that we have chloride ions on both sides. We notice that we have calcium ions on both sides of the equation. So our net ionic equation then will look like this. I'm not writing in the aqueous. Okay, now we can reduce those coefficients. We'll go ahead and do that. I'll just take them out. And again, this is our net ionic equation. As I said before, for a strong acid, strong base neutralization reaction, our net ionic equation is always going to look like this. Let's take a look at the neutralization reaction of hydrocyanic acid and potassium hydroxide. First thing I'm going to do is write out the overall reaction. Potassium hydroxide is a strong base, so it's aqueous. So we're going to end up with a salt. Remember, hydrogen ion will be released. That will form water, and then our salt is going to be potassium cyanide, which is soluble. So now I can write my ionic equation. Now remember, this is a weak acid. It does not completely dissociate, so I have to keep it together here. My potassium hydroxide will be dissociated completely into potassium ions and hydroxide ions. My potassium cyanide will also be dissociated. It's a soluble salt. So potassium and cyanide ions. And then, of course, we have water, which we know doesn't dissociate. Notice here the only ions that cancel out are the potassium ions. So my net ionic equation would be the hydrocyanic acid plus hydroxide ion, because we still have some of this in solution. It does not completely dissociate. It's a weak acid. Then here we have cyanide ion plus water. So that is my net ionic equation. Okay. And let's do one more. Let's see. We have acetic acid and sodium hydroxide. So let me erase this. So again, acetic acid, that looks like this, plus sodium hydroxide, that's completely dissociated. And we're going to end up with, again, a salt and water. I'll put my water over here. We're going to end up with sodium acetate. So sodium acetate. And that is soluble. Now, I can write my ionic equation, but remember, acetic acid is a weak acid. It does not completely dissociate. So this has to stay together. My sodium hydroxide does dissociate. Okay. And turns out that sodium acetate also dissociates into ions, and then we have our water. And let's see here. Only the sodium ion cancels out. And our net ionic equation then is acetic acid plus hydroxide ion to yield. We have our acetate ion plus this. This is our net ionic equation. Now, some acids and bases will react to form salt, water, and also a gas. Those are anything containing carbonate, sulfite, so hydrogen sulfite, sulfite ion, or sulfide ion, so hydrogen sulfide and sulfide ion. Carbonates will end up with carbon dioxide and water. The sulfites, hydrogen sulfite and sulfite, sulfur dioxide and water. And then our sulfides will end up with H2S gas, okay? Actually, that's very toxic. Anytime you work with anything that produces H2S, you have to work in the hood. Let me show you how that happens with the carbonate. So here we have sodium carbonate and acetic acid. So what happens is, remember, you got a weak acid, and it's going to partially ionize, and what'll happen is we'll have the sodium bicarbonate that will ionize completely. What we'll end up with is sodium acetate and this carbonic acid. The thing is, carbonic acid, it's not very stable. It decomposes to water and carbon dioxide gas. So we can rewrite this then as sodium hydrogen carbonate plus we're going to end up with sodium acetate plus water plus CO2 gas. Okay, so that's how you would write the overall equation. I'll let you go ahead and do the ionic equation. And so, you know, it's the same here. What we would end up with here is sulfurous acid, and the sulfurous acid will decompose to sulfur dioxide and water. Okay. So the next type of reactions that we're going to look at are precipitation reactions. And we all know that sodium chloride is soluble in water, but there are limits as to how much sodium chloride will dissolve in a given amount of water. So at 25 degrees Celsius, the limit is 35.9 grams of sodium chloride in 100 milliliters of water. If I try to dissolve 37 grams, only 35.9 grams will dissolve in that 100 milliliters at 25 degrees. The rest will remain undissolved. We say that sodium chloride is readily soluble in water. Some ionic compounds, some salts, are not considered soluble in water. So for example, silver chloride, it is insoluble in water. If the maximum concentration of a solute is less than about 0.01 molar, then we say the solute is insoluble in water. Silver chloride would be considered insoluble. So what happens is, let's say I have two aqueous solutions. I have an aqueous potassium iodide solution, and potassium iodide is soluble in water, so it's completely dissociated into potassium and iodide ions. And let's say I have a solution of silver nitrate. Okay, again, it's aqueous, completely soluble, and so this would be dissociated into silver and nitrate ions. Okay, so I have these two solutions, and then what I do is I mix them together and I end up with something like this. I notice that there's something forming here, a solid, or what we call a precipitate. So if I were to mix aqueous solutions of potassium iodide and silver nitrate together, I'm going to get this precipitate, and that precipitate is silver iodide. Okay, let's go ahead and take a look at what we have here. I've mixed aqueous solutions of silver nitrate and potassium iodide, and I end up, I'll put an S here for solid, with a precipitate of silver iodide, and we have aqueous potassium nitrate. Let me go ahead and crudely draw this. Okay, here's my solution with potassium ions and iodide ions, plus my solution of silver ions and nitrate ions, and we put that together. Okay, so what we have is we have this solution now that has silver ions, potassium ions, nitrate ions, and iodide ions. Well, here's what happens. One of the reasons why, for example, potassium iodide dissolves in water is because the attractions between the ions and the water are greater than what the attractions are between the ions. Now in this case here, what happens, my silver and my iodide ions get together and they form a solid, this precipitate. And what we have is, we have this solid silver iodide, and then we have these potassium and nitrate ions that are in solution. They're completely dissociated. What that means is that the silver and iodide ions have more of an attraction for one another than they do for water molecules, which is why they form that precipitate. I have my overall equation here. They also call this a molecular equation, even though there are no molecules involved, but that's what they call it. So I can write an ionic equation. I know this is dissociated, this is dissociated, so we have silver, nitrate, potassium, and iodide ions. And then as I just showed over here, my silver iodide is a precipitate, it's a solid. And my potassium and nitrate ions are dissociated in the solution. Now, watch what happens here. I have nitrate ions on both sides. Oops, this should have a negative charge here. I have potassium ions on both sides, so those cancel out. And my net ionic equation, I have this left here. So the actual reaction is between the silver and the iodide ions to produce solid silver iodide. The potassium and the nitrate ions are called spectator ions. They're there because I needed some salt source. I needed two salt sources, one to give me iodide ions and the other to give me silver ions. I would have had the same result here if I would have used sodium iodide. So I could have used sodium iodide, and I could have used, I don't know, let's say silver acetate. And it would have been the same thing. I would have had one solution with sodium and iodide ions, another solution with silver and acetate ions. So I'd have the silver ions, the iodide ions, the acetate ions. What else did I have here? And the sodium ions. Again, the silver and iodide ions have a stronger attraction for one another than they do for water molecules. They would have formed a precipitate, and I would have been left with sodium and acetate ions in solution. They would have been the spectator ions. I would have still ended up with a net ionic equation of silver ion plus iodide ion to produce silver iodide. These, the acetate and the sodium ions, would have been the spectator ions. This is where the solubility rules come in. You don't have to memorize these. I will give you these on an exam. But here's how it works. Here we have the soluble compounds. Okay, so all the soluble ionic compounds. So all the compounds of groups 1A ions are soluble. So anything that contains a group 1A, sodium, potassium, cesium, any compound that contains those is going to be soluble. All compounds that contain ammonium are going to be soluble. All nitrates and acetates and perchlorate compounds are soluble. All chlorides, bromides, and iodides are soluble, except when they are combined with silver ion, lead ion, copper ion, and this mercuric ion here. All fluorides are soluble, except for lead-2 fluoride and fluorides of groups 2A, so magnesium fluoride, calcium fluoride. All sulfates are soluble except for calcium sulfate, strontium, barium sulfate, silver sulfate, and lead-2 sulfate. Everything else you can consider insoluble. Okay? So all metal hydroxides, all common carbonates and phosphates, all common sulfides. Unless they're combined with group 1A metals, okay, then they would be soluble. So anything with sodium is going to be soluble. So these are the solubility rules. For example, if I ask you, is sodium phosphate soluble? Well, we see the phosphates are not on this list, but sodium is with it. So yes, this would be soluble. Okay. Is calcium carbonate soluble? No, carbonates are insoluble. It says so right here. But sodium carbonate is soluble. Right? It's a group 1A metal. So now we see that we have two beakers or two solutions. One has aqueous sodium iodide and the other aqueous lead-2 acetate. What happens when the two are mixed? Does a reaction occur? So what we're going to do is we'll write the equation. So we have sodium iodide, and we know that this is soluble, so we'll write that as aqueous. Plus we were told that, but if you look at the solubility rules, you know that. And we have lead-2 acetate, so lead, I'll just do the acetate like this. That is also aqueous. So we mix those two together, and what we do is replace the sodium ion with the lead-2 ion. So I'll write that formula as lead-2 iodide. You have to make sure you get the right formulas here, okay? And then we'll replace the lead with the sodium, and we have sodium acetate. So now I check my solubility rules. I know sodium acetate is soluble, so it's completely dissociated into ions. and I look at my lead 2 iodide, and I know from the solubility rules that lead 2 iodide is insoluble. So that means we have formed a solid. Now, I want to make sure that my equation is balanced. So I'll put a 2 here, and I'm going to put a 2 here. I forgot to put my 2 here. Okay, and we'll put a 2 here. So now it looks like we are balanced. So next, I'm going to write my ionic equation. I know this is completely dissociated, so we have 2 sodium ions plus 2 iodide ions. And the lead acetate is also soluble. I have 2 acetate ions. Now, the lead 2 iodide is a solid, so this has to stay together. And then sodium acetate, we know, is soluble. Again, you can always check those solubility rules. Okay? So let's take a look, see what we have here. Our sodium ions cancel out. Our acetate ions cancel out. And what I'm left with is 2 iodide plus lead to produce lead 2 iodide. So the reaction takes place between the iodide and the lead ions. So yeah, we have a precipitate form. So a reaction did take place here. Let's take a look at this next one. We have aqueous solutions of potassium nitrate and ammonium chloride. We mix them together. What is the result? Is there a reaction? I think some of you are looking at these two now, and just by looking at them, you realize that there is no reaction. NR, no reaction. Now, for some of you that don't see that, let's go ahead and write the equation. So we have potassium nitrate, that's aqueous, plus ammonium chloride, aqueous. And again, we go ahead and put the ammonium cation with the nitrate. So we have ammonium nitrate. Oops. Let's get rid of that. Okay, so ammonium nitrate plus, we'll put the potassium with the chloride. And we know that ammonium nitrate is going to be soluble, so this is aqueous. And potassium chloride is soluble, so it's aqueous. So in other words, no reaction took place. We have a solution that just has ions. Let's go ahead and write the net ionic equation. Potassium ions plus nitrate ions plus ammonium ions plus chloride ions gives us ammonium ions plus nitrate ions plus potassium ions plus chloride ions. They all cancel out. There is no reaction. We did not form a precipitate. Let's see what happens when we mix aluminum sulfate and sodium hydroxide. So we'll write the overall equation. Aluminum sulfate plus sodium hydroxide. We know both are soluble, so we write them as aqueous. And again, we'll just switch cations. So we'll put the sodium with the sulfate plus aluminum goes with the hydroxide. You have to make sure you write the correct formulas. Now what I'm going to do is balance my equation. So I have 3 hydroxides here. I have 1 here, so I'm going to put a 3 here. Let's see, aluminum. Let's go ahead and put this here for aluminum. So we have 2 aluminums on both sides. We have 2 times 3, 6 hydroxides. So I'm going to put a 6 here. and I'll put a 3 in front of this. So we're balanced. 2 aluminum, 2 aluminum, 3 sulfates, 3 sulfates, 6 sodiums, and 6 hydroxide. We're good. Let's see, is sodium sulfate soluble? Yes, according to the solubility rules it is. Okay, good. And aluminum hydroxide is insoluble. So a reaction has taken place here. Let's go ahead and write the ionic equation from this. So we have 2 aluminum ions plus 3 sulfate ions plus 6 sodium ions plus 6 hydroxide ions. And that's going to give, let's see, 3 times 2 is 6 sodium ions plus 3 sulfate ions. And then, of course, the aluminum hydroxide is insoluble. That's a solid. So our net ionic equation, the sulfates cancel and our sodiums cancel. So sodium ion and sulfate ion are spectator ions. And what we have is our net ionic equation, which shows the reaction between the ions. 2 aluminum plus 6 hydroxide. I should put the aqueous here. And that gives us 2 aluminum. I forgot the 2 there. So 2 aluminum, 2 moles of aluminum hydroxide. So let's see. Can I reduce this? Yeah. So we have aluminum, 1 mole of aluminum ions plus 3 moles of hydroxide ions to produce aluminum hydroxide solid. So practice writing those ionic equations, both the ionic and the net ionic, and be able to predict if a reaction does occur, and if so, what are the products. The next reactions that we're going to talk about are oxidation reduction reactions, or redox reactions. I'm going to go ahead and finish up this chapter in the next video.